All right, we're live. All right, start stream. Boom. So I'm gonna work on finishing chapter 9 today. I'm gonna get preview open here. Chapter 9. I was on this protic, aprotic stuff. I think I did read some of this. This is SN1, SN2 reactions, if I recall. And I want to. There's so much intense thinking that goes on in these organic chemistry. Speed run through a chapter in an hour on a live stream. Things that I'm doing that I want to just mentally prepare better. I think that'll help. I think it's worth a 2-minute investment, 1-minute investment. I'll just give it 1 minute today. So I'm going to just literally close my eyes and visualize myself going through this really quickly, being highly energized and making sense of these things quickly so that I'm able to solve problems and do well on the Feynman method checklist that I do with AI at the end of each chapter. So let me go begin that. Set a 1-minute timer. Okay. High energy the whole stream. Reading quickly. Terms connecting. Nucleophilic attacks. Electrophilic. Mechanisms making sense. Visualizing this in real life. I like to do some 5-2-7 breathing. That's 5 seconds in. Hold for 2. Exhale for 7. All right, there goes my minute of visualization. I'm ready. SN1 and SN2 reactions are going to make sense. So I want to look through the focus questions here. Draw and label the full SN2 mechanism. What type of stereochemistry results? Draw the SN1 mechanism. Why does it lead to racemization? So this is an SN2 reaction. We have a nucleophile that attacks this electrophilic center. There's a leaving group that has an electron leave with it. The nucleophile goes in. There's an H and then the rest of the atom. And so I need to get this SN2 diagram down. And then SN1, let's see the difference. SN1, there's no nucleophile attacking. It's just the leaving group goes with the electrons. There's no lone pair. Then there's going to be the leaving group So what's the meaning of 2 in SN2? If the nucleophile is good enough and if all other conditions are just right, a reaction can take place in which the configuration of the chiral center is inverted by bringing the nucleophile in one side and kicking off the LG on the other side. Now we get to the meaning of 2 in SN2. Remember, I'm high energy. Remember from the last chapter that nucleophilicity is a measure of kinetics, how fast something happens. Since this is a nucleophilic substitution, the rate of reaction is dependent on the concentration of nucleophile and electrophile. It's second order because it depends on both the nucleophile and the electrophile. This is first order. S1 process has 2 steps, so it's 2 humps in this thing right here. There's this first step where the leaving group goes. Then a nucleophile attacks and goes on here. Nucleophile that is has a lone pair. The one simply means the rate is not dependent on the concentration of both. The rate is only dependent on the concentration of the electrophile. Okay. That makes some sense. To understand the meaning of the 1 in SN1, we must focus. Oh, man, this is so hard. Okay. Let's see if I can draw this quickly. I need to just open cursor briefly. I don't want Mac Anki. I want this. I want to go. Actually, I can go to terminal for this. Hide cursor, go to terminal, go here. All right. So SN1 is going to be, you have R, you have H, you have R, and I think it's like this, this, and this. And we have this center. And for SN2, there's a nucleophile right here that attacks right here. And it leads to, oh yeah, there's a leaving group. LG minus goes away. And then we have this with a nucleophile on the other side. Whereas this one is 3 steps. Let me just look at the diagram. I'll double check my work. R1, R2, H. Okay, H and R1 are the ones that are opposite each other. Combining this with chirality is what's tricky. By the way, I have visualized success. That's good. Since this one does this one have an electrophile? The substrate is primary. So we predict an SN2 reaction. I need an explanation for that. What does that mean, and how does it make it SN2? Putting on voice control too. So I tried doing these the other day, but it was way too tricky. The leaving group is chloride. The carbon that is attached to one other carbon from the cyclohexane ring and 2 hydrogens they're implied. That makes it a primary carbon. Primary carbon is bonded to only one other carbon atom. Okay. Why does primary favor SN2? If it's uncrowded, like a primary carbon, then it can happen easily. If it's crowded, though, the backside attack is blocked by sterics. That helps a bit. Okay. So this one, I presume, is going to be SN. Is that SN1? Let's see. Nope. The substrate is secondary, so it's SN2. So I guess if it's primary or secondary, it's SN2. Let me look for primary. First appears here. The substrate is primary if there are 2 alkyl groups. So primary substrate is better. So it's only if it's tertiary. So look at the carbon here, and this is tertiary. There's 1 carbon group, 2 carbon groups, 3 carbon groups attached to this carbon. For this carbon, there's bromide. This is secondary, so it's SN2. This is primary, so it's SN1. Let me just see if those are right. Primary, secondary, tertiary. Okay. That actually makes sense. This is positive, a positive development here. Then in the compound below, circle the leaving groups that occupy a benzylic or allylic position. This I need to understand better. And I need to understand what benzylic means. This is a benzylic position, and this is an allylic position. Resonance. If a carbocation is resonance stabilized, then it will form more readily. So this carbon is stabilized by resonance. So because this double bond can move here. Yep. It makes the leaving group willing to leave, and we can have an SN1 reaction. Got it. Alg in a benzylic position, Alg in an allylic. See a double bond near the leaving group and are not sure, just draw the carbocation that would form upon the loss if the carbocation is resonance stabilized. So this, I believe, would be allylic, right? Are all these allylic? This is allylic. It has to be one away, though. This is allylic right here. Let's see what they circled. Okay, I need to get an explanation for this too. They don't explain much in this textbook at this point. Explain how I know that these groups are all right. Let's see how that goes. Allylic if it's adjacent to a double bond. Leaving group is on a carbon that's next to a double bond. Benzylic if it's adjacent to a benzene ring. Okay. The left BR is allylic because it's adjacent to a double bond. Owen Whitty is asking if I ever work with Grok. Yeah, Grok is great for OChem, I found. I was actually going primarily Grok at first because ChatGPT was not going well. I found Grok to be better. But now I'm going back to ChatGPT. It's just sort of my default. And I am using Grok now. At the end of each lesson, I summarize what I learned and have ChatGPT put it into a tweet thread. And then I use Grok when I'm just on my phone on Twitter. I'll go back to the tweet thread that I post and ask Grok to clarify each of the points, which is helpful. So that's in a little like subtle way I can, just by twiddling my thumbs, review each lesson. So I'm not using it as my primary AI, but I am using it still. I want to use Grok more in future learning challenges that I undergo. Specifically, Grok's tagline, I think, on its homepage is understand the universe. And that's one of the sort of, that's the goal, what I'm building up towards. It'll take a while. I'm still linear algebra, organic chemistry very early on. But for some of the deeper theoretical physics stuff, I want to try Grok for what it's worth. So these are both, this is benzylic and this is allylic. This carbon here is not adjacent. This one is adjacent to the double bond. This one is adjacent to the benzene. This one is part of the benzene. This one is part of the double bond, so that doesn't count. Okay, I think I get it. Determine whether loss of the leaving group would result in a resonance-stabilized carbocation. So if I lose this leaving group, I just have this benzene ring. I think that this is a resonance-stabilized because these double bonds can move around. Let me double check what the answer is. The leaving group does not occupy a benzylic position. I get that. In order to be benzylic, there must be an sp3 hybridized carbon. So it's basically if there's a benzylic or allylic group. This one is. It's benzylic. This one is not. This one is. It's allylic. Wait, it was 9.8. Yeah, 9.8 is. These resonance structures are crazy though because they get this. There's the double bond, and there's a lot of different structures here. 1, 2, 3, 4, 5. I do understand all those resonance structures though, I think. So this is not stabilized by resonance. This one is. It's allylic. Okay. I get that too. This is positive so far. Nice. It helped previewing this yesterday, even though it made no sense. Now I'm sort of in a place to make sense of it. And I want to get to chapter 10 today too, the nucleophile. So these are all these common nucleophiles. This is something I probably should memorize. Identify whether the following nucleophile will favor SN2 or SN1. It has a sulfur atom with lone pairs. If it's strongly nucleophilic, that favors an SN2 reaction. This is 12 is SN2. It's a strong nucleophile, RO. OH is a weak nucleophile, so I assume it's SN1. Yeah, alcohol. Okay, I do remember these ones. Now the leaving group. Okay, so what are these factors for these things? There's the nucleophile. I get the electrophile. And that's the allylic benzylic stuff. I think I get the nucleophile. Basically, I need to figure out. Well, I'd like to understand why each of these are strong nucleophiles or weak nucleophiles. Why is fluorine a weak nucleophile, for instance? I would think that would be strong. Explain why some of these are strong nucleophiles and why some are weak nucleophiles. Nuclear files. The dictation really can't handle the weird words you get very often in organic chemistry, like nucleophile even. So the leaving group. Okay, the leaving group. And we want it to be a weak conjugate base. Iodide is one of the best leaving groups because it's the most stable conjugate base. They go with the strongest acid. Then these bad leaving group, good leaving group. This is the bad leaving group with hydroxide. This is the good leaving group with H2O. So sulfonate and halides are the most common things to see. Iodide's the best leaving group. Identify the leaving group in the following compound. I assume it's Cl. Hydroxide, not a good leaving group because its conjugate acid is not a strong acid. Okay. Best leaving group in each of the following structures. I assume it's the sulfonate, which is in this case OOOCH3. Is that mesylate? Yeah. Let's see what 9.19 says. Mesylate is a good leaving group. Ethoxide is a very poor leaving group. Is ethoxide anywhere here? Let's see what ChatGPT said to this answer. I'd like to understand. So negative charge makes it, more electron rich. Low electronegativity, that's why F is not there. Less greedy, more willing to share electrons. Polarizability, large atoms, okay. Less solvent stabilization, polar aprotic solvents. Small and highly electronegative is why F doesn't work. And then these are neutral with no charge, so they're less reactive electron donors. Okay. That makes sense. Now we get the solvent. Factor for the solvent. Okay, this is where it's protic or aprotic. These are aprotic. Whenever a solvent is indicated, you should see if it's polar, aprotic, and if it's going to be SN2 if so. So is this SN1 or SN2? Well, this has DMSO, dimethyl sulfoxide, chloride, so I assume that would be SN2. Polar, we expect an SN2 even though the substrate is secondary. Yeah. Okay, polar aprotic, got it. Using all four factors, this is where it gets crazy here. SN2 inverts the chiral center. SN1 will make a racemic mixture. Another major difference, carbocation intermediate, okay. So it's the competing factors. Steric and electronic effects are the big thing. So stuff with electrons and stuff with the size of the particles. These final sections are good to actually read. I think they're pretty dense. All right, just finished reading that. Now, Owen asking some good questions here. What inspired you to start this journey? I was just sitting, walking, doing whatever one day, and I decided I wanted to learn. Well, I've always wanted to learn linear algebra. You should watch my full video on YouTube about learning linear algebra where I explain this more in depth, but I always wanted to learn linear algebra. I dropped out of college, and I've always sort of fantasized about getting into higher math. Linear algebra I know is important for some concepts in machine learning and other ways of understanding the universe. And I hadn't taken a math class in a while, and it was uninspiring. I'd considered signing up for community college class, signing up for a Coursera course, doing something like that, but it's not really inspiring. And what inspired me specifically was the deep research function on ChatGPT. I forget what it was. I put something in. I said like, oh, I have X amount of days before this exam. I was helping a student out. How do you recommend I study? And I realized ChatGPT deep research was great at setting up a curriculum. And I hadn't heard of anyone ever who had tried to set up a curriculum to learn something as complex as linear algebra, especially in the very short time span, like 30 days, which I did. And so I just like the challenge of it. And I've been learning with AI, I'd say, since the day that GPT-3 came out. I was amazed by that. Obviously, the first thing people were doing was making silly poems and messing around with all sorts of stuff, just playing with it. And I was afraid that it was this work replacement tool at first, AI, but as time went on, I've realized it's more and more like my TA when I'm tutoring. It can provide really, really good assistance. As a tutor, with someone with 15 years of experience, really strong intuition as a teacher, and a lot of science behind the methods that I usually employ to teach can guide it pretty well. And I wanted to do the challenge as the short of it. How long have I been using AI for learning? Yeah, since a couple of years now. But for this is my second month of doing designated curricula on AI and live streaming it 1 hour per day, which has been a really nice thing for me. I'm always really pumped up after I finish live streams, and I'm really bummed on the few days that I haven't live streamed. I feel guilty about it. And yeah, so I got into linear algebra just because it seemed like it'd be hard. And if I could learn linear algebra, I could learn just about anything. And organic chemistry was the next hardest course that I hear about in college. So thought I'd give that a shot. Going back to this, look at all the reagents and conditions, determine if it will proceed by SN2, SN1, or neither. So this one doesn't have 9.30. Let me look at 9.29 first. It's benzylic. So it'll be SN2, I think. Primary substrate. Strong nucleophile, yep. The leaving group is good. Solvent is not indicated. All right, this one we have DME, which is a solvent that makes it SM2. We also have we don't have a good leaving group. We have Cl, it's not benzylic or anything. We have hydrogen sulfide. I don't think that's a strong nucleophile. I think that it still is SN2 though, with those factors considered. Let's see what 9.30 says. Substrate is secondary. Oh yeah, secondary substrate, C and C. Reagent, oh, it is a strong nucleophile, and the solvent is polar aprotic, so all of that favors SN2. I was right about SN2, but not 100% about all the reasons. Looking at this one. Wow, this makes so much more sense than yesterday. This is really encouraging. For each reaction below, look at all the reagents and conditions and determine if the reaction will proceed via an SN2 or SN1 pathway or neither. Oh, why am I reading the instructions again? Okay. Cl, it's this is going to be SN1 because it's tertiary. That just kind of crosses out everything. Plus H2O, weak acid. Yeah. Substrate tertiary reagent is weak nucleophile, I mean to say. SN1. Yo, I'm getting these. Let's go. All right, I'm going to hop to the end because I'm feeling cocky. Okay, well, this is a sulfonate, so that means that it's a polar aprotic solvent. And the C is tertiary, though. Oh, so that means that it's going to be SN1 because tertiary overrules the aprotic solvent for 9.35. Reagent is a weak nucleophile. Oh, the reagent, the mesylate is actually, I guess, something that favors SN1. Interesting. So I got that part of it wrong, but I was still right about SN1. This one is SN2. It's a secondary. No, it's primary. Primary, chloride is strong, DMSO, dimethyl sulfonate. Great. Okay, guys, I'm ready for the Feynman technique time. I'm going to start answering the curiosity checklist for chapter 9. Number 1, the full SN2 mechanism results in stereochemistry with an inverted chiral center. The SN1 mechanism leads to racemization because... Explain that to me a little bit. So that's one of the few things this unit that doesn't really make sense is how we get the racemization. How do you pronounce that word?
Racemization.
Racemization. Attacks from the backside. Leaving group leaves attacks. So it's like flipping an umbrella inside out. Interesting. Backside attack, it's inverted. Okay, that's helpful. I like this. It's like that. Leaving group leaves. Planar carbocation. Nucleophile can attack from either side of the flat carbocation. Oh, that's why. Okay, it's because it makes it sp2 hybridized. It's planar. It's not like the inverted umbrella. These are helpful examples. Good. Even though it can't draw me visuals or show a 3D visualization, that was a good explanation. Thank you, ChatGPT. Let's go back to the curiosity checklist. Going for number 3 through 5 now. Number 3 in the curiosity checklist. Make sure to grade me and be a perfectionist and give specific feedback about what might be missing from my answer. Number 3, steric hindrance shuts down SN2 for tertiary substrates because of the lack of space to attack from the backside. It has to instead create an intermediary carbocation. Number 4, a tertiary carbocation is more stable than a primary one because there are bigger groups on each side. And I believe then there's going to be more overlap of orbitals. Clarify for me on that answer, though. I'm not certain. And number 5, resonance affects SN1 by making something more stable and favoring the SN2 reaction. Again, explain why that's true, though. The dictation is all over the place always. I'm just going to let it rip. What is NaCl? Read in the comments. What is NaCl, and should I add it to my French fries? Well, great question. NaCl is sodium chloride, which is a salt. I'm just using high school chemistry knowledge. Apparently this commenter, Adam Moelis, doesn't really know high school chemistry well. That's fine. We're not judging anyone. Anything that is an ionic compound is technically considered a salt. So NaCl, even though that's what we normally think of as table salt, it could be MgCl2. It could be anything with a cation and an anion. I say, yeah, add it to your French fries. It's delicious. But also keep in mind, French fries are not healthy. Fried foods in general, I used to think that was sort of a myth. Fried foods bad, but all the seed oils that they fry stuff in, it's I know with direct experience with someone in the restaurant industry that you can't afford to use good ingredients like beef tallow or non-seed oils to fry food because you need a ton of oil to deep fry something. So French fries are bound to have a lot of seed oils input into them, put at really high temperatures, which therefore creates really high omega-6 content, which can cause inflammation in your cells and lead to a lot of long-term negative health effects. So avoid French fries if possible. There's better ways to eat potatoes, baked potatoes, a lot of different ways. But French fries are nice every once in a while. You know, don't be crazy but add a little salt when you do. Salt is underrated for your health too. NaCl is nice. Our bodies need salt. Salt got a bad rap. I don't know why. And omega-3s are good too. Omega-3s are great. You know, we generally, it's about the balance of omega-6s and omega-3s. Omega-6s aren't bad on their own. It's just the American modern food diet tends to favor them because cheap seed oils and things are rich in omega-6s. And it's when you have an imbalance of those that it's really bad, from my understanding. Omega-3s you get from, avocado or pistachios or cashews or olive oil. A lot of things have the omega-3s, which are kind of like the good fats that have a lot of health benefits for our thyroids, for our hormonal balance, all that stuff. Owen's asking if I have premium plans on either Grok or ChatGPT. Yes and yes. You might see this little pro in the corner. I'm one of those guys who pays $200 a month for ChatGPT. Yeah, I find it worth it. I find it well worth it. And I have X Premium as well, so I get the Premium Grok. It's just $16 a month. There's probably a higher plan on Grok I could get, but I don't use it enough to be worth it. I also have Claude Plus, the $20 a month, not the super $100 a month. I also have Cursor paid for on the plan, Cursor Plus, whatever it is. I pay for a lot of these AI things. I'm going to actually clean up some of my subscriptions soon because I feel like I'm probably overpaying. And if I were really legit, I'd probably like run them locally and not pay anything and have my own server. Well, I want to get into that this summer. All right, I got a B on this. Hysterics prevent backside attack, but SN2 doesn't switch to SN1. The pathway depends on the reaction conditions. SN2 is blocked because 3 bulky R groups around the electrophilic carbon create too much spatial crowding for the nucleophile. It requires a direct orbital overlap to displace the leaving. Wow, this is intense. I basically get that, though. Why is a tertiary carbocation more stable than a primary one? Bigger groups on each side, more overlap. Yeah, not orbital overlap. That's the stabilizing factor. Okay. Electron donation, hyperconjugation, inductive effects. Tertiary carbocation is more stable because it's surrounded by 3 alkyl groups, which are all electron donating. They delocalize the positive charge via hyperconjugation, not a word I've been taught. Overlap of the sigma orbitals with empty p orbital. That's intense. I got bad grades on all these. Resonance makes something more stable. I guess I asked it to be a perfectionist. That's good. Makes something more stable and favors SN2. It does not favor SN2. Whoops. It stabilizes carbocations, which are intermediates in SN1. Okay. Resonance is for SN1. Got it. Nucleophilic effects. Time for number 6. Let's go. Number 6. A nucleophile's strength matters in SN2 because it has to be strong enough to overcome forces for the backside attack. But in SN1, it does not matter. The only factor that matters is the strength of the electrophilic center. It's partially why it's called SN1, because it's dependent only on one factor. And the nucleophile will be able to attack from either direction after the carbocation is created. Number 7. I think OH- is a stronger nucleophile because it has a negative charge. Number 8. I- is stronger than F- as a nucleophile, even though it has lower electronegativity because it is much larger. And F- is going to be too compact to donate its electron. Oh, wow. Oh, and you got Super Grok annual subscription. Dang. ChatGPT for $200 a month sounds steep. How it is? Oh, it's annual for $300. So that's $25 a month. Super Grok. Curious. What makes it worth it to you? I'm not sure if ChatGPT is worth it for me. I have used Sora a few times in videos. It's nice. I have I find the deep research to be the most useful thing. I use at least that once a day, but I underuse it honestly. So it might not be worth it to have Pro. I need to get more into having it use the operators and other things. Like there's, I kind of just got it aspirationally to use ChatGPT more. You know, sort of the sunk cost fallacy at work here, where I put all this money in, I better remember to use it. I recently set it up so that on my phone I have this new action button on the iPhone 16, and I just press and hold that, and it immediately will dictate it to ChatGPT. So that's my new default for going around and wanting to ask a quick question. But yeah, very helpful. Oh, I did way better on these. A minus AA. I hope maybe it just was, okay. Strength of the electrophile isn't the key SN1 factor. Stability of the carbocation is. Okay. Rate determining step in SN1 doesn't involve the nucleophile at all. Got it. It's a concerted step in SN2. The loss of the leaving group is the rate determining step. So it's the leaving group that matters. Which is stronger? OH minus is stronger. That's right. More nucleophilic than neutral. Okay. Why is it larger and more polarizable? Yep. I didn't say more polarizable, but I'll take it. Better stabilize its negative charge while still donating. Hold its electrons. Heavily solvated. Okay, yeah. That's all good. So yeah, and I figured ChatGPT, I mean, they're constantly launching new features that are only available to the pro tier. And so I like getting early access to those things. I also share my account with some people, so it's nice to all chip in with that. Hope that's not against the terms of service, but sorry, OpenAI. You're going to be like $1 trillion company anyways. Hopefully you can survive people sharing passwords. They don't crack down on that at all. So, okay. Oh, whoops, I went up too high. Stereochemical outcomes. Oh gosh. Here we are. Number 9, what makes a good leaving group? A good leaving group is something that has a strong conjugate acid. So it's a weak conjugate base. OH minus is a bad leaving group because its conjugate acid is H2O, which is practically neutral. It can be converted into a good one, though. I'll explain that. How could OH minus become a good leaving group? Number 11, polar aprotic versus polar protic. Polar aprotic is polar means that there's one side that's positive, one side that's negative. And aprotic is about having a proton that can be donated. Explain to me protic and aprotic, though. I know polar protic, I think, is like the sulfonates and stuff. Give me examples, too. And polar aprotic solvents, I see now they got that backwards, speed up SN2 reactions because they enable a backside attack, but explain how that happens more. Oof, I'm already 43 minutes into the stream. I'm taking my sweet time. This method isn't super fast always. It's not neutral. It's a weak acid, though. Okay. Good leaving group is the conjugate base of a strong acid. Good. Nucleophile availability is the key here. Okay. Whew. Okay. Well, it totally didn't answer most of my things. What? I guess it was some jumbled dictation there. Yeah, what's some of the new features? Sora is good for video generation with ChatGPT. I know there's probably free things online or cheap things online, or the new Google stuff. I just got the Google AI subscription, just a free month, but I don't like it for some reason. For some reason, the Google stuff always irks me. It just feels off. It doesn't give me good replies. I think it's overrated. I don't know what the benchmarks are. It's saying it's better than everything else, but not for me so far. And Google AI Studio's interface sucks, in my opinion, compared to Cursor or other things for coding. I'll tell you one thing I like about ChatGPT. Maybe Grok has it too, but I like that there's widgets for it, so it's programmable as the button, the action button on iOS. It's a small thing, and yeah, it works well. Also, give me answers to 10 and 12. I was answering all of them, idiot. Okay. Let's go to number 13. Number 13. if you have a secondary substrate, a weak nucleophile, a polar protic solvent, I think you would have SN1, because even though the secondary substrate favors SN2, the weak nucleophile and polar protic solvent favor SN1. Number 14, the factors that matter most for SN1 and SN2, the most important is strength of nucleophile, and then the loss of the leaving group, and then the solvent. And actually the most important is, what was it? Whether it's primary, secondary, or tertiary. See how that goes. It is a strong base and it's unstable on its own. Okay, its conjugate acid is weak. So how do you make it a good leaving group? Oh, you protonate it with a strong acid. Okay. Becomes H2O, which is neutral, much more stable. H2O is an excellent leaving group. Got it. Polar aprotic solvents do not hydrogen bond with nucleophiles. More reactive and can attack the electrophile more easily. Polar aprotic solvents increase SN2 rate. So I probably got that wrong. Weak nucleophiles favors SN1. Polar protic solvent. What did it just say? Yeah, polar protic favors SN1. Substrate structure, then nucleophile strength, then solvent type, then leaving group ability. Don't put leaving groups or solvent above substrate. Yeah, I didn't mean to. That's fine though. Let's go to number 15. I want to answer the rest of them in this one prompt. Number 15, racemization means that the nucleophile will attack equally from the front and back, meaning that the chiral center will have equal parts R and S configuration. Number 16, inversion is guaranteed in SN2 because of the backside attack, which flips the configuration of the chiral center. But please explain what retention means. I'm not sure. Number 17, a hydride or methyl shift will occur in SN1 because I'm not sure. Just answer 17 and 18. What are rearrangements exactly? Okay, thank God. I'm done with chapter 9. Good riddance. Let's speed run chapter 10 now. Close chapter 10. That is page, oh, it's another long chapter. Not too long. 15 pages. Okay, elimination reactions and then addition reactions. Okay, so just different types of reactions. Chapter 11's a long one though, so I should try to finish this quickly. 157. Okay. Good to remember this is 12 pages off. Oh yeah, let me make a copy. I'm going to try something different for chapter 10, actually. So, nucleophile attacks from both sides, 50-50. Nice. Retention is configuration stays the same. Oh, yeah. After the leaving group departs, you have the carbocation. If it's secondary, an adjacent carbon has a hydrogen or methyl group, that group can shift over with its bonding electrons to create a more stable carbocation. Carbocation rearrangement only happens if the new carbocation would be more stable. Who makes better recipes, ChatGPT or Grok? I haven't used it much for cooking. I still use the old-fashioned internet, like their specific blogs. I don't cook that much. My wife is an amazing cook, though. My assumption would be ChatGPT. I just think their training's a little better for that, probably, but I think they're both probably pretty good. Having Reddit helps with ChatGPT. I don't think people post recipes that much on X, which is the main competitive advantage I can see for Grok. That's a very basic way of looking at Grok versus ChatGPT. Okay, hydride or methyl shift. More stable carbocation. Resonance stabilized. Rearrangements are structural shifts that occur after carbocation and SN1. Got it. It's only, okay. Here is chapter 10. Give me a quick preview of the concepts in the chapter, a curiosity checklist to ensure my mastery, and a quick glossary of important key terms I should understand to make sense of the chapter. That's the new thing I've added. I think the glossary will be really helpful. There's a lot of key terminology here that I should get before I dive into the chapter. So doing that, let's see how it goes. Chapter 10. Let's go into the top. So this is about these elimination reactions. So I have an alpha and beta. Elimination, substitution is substituting this thing. Elimination is getting rid of it. Pretty straightforward. Elimination, the beta proton is removed together with the leaving group, forming a double bond. Okay, so it forms a double bond. There's E1 and E2, starts with E2. Base removes a proton, causing the simultaneous, so this is another one of those things where it's two things happening at once, proton transfer and loss of a leaving group. All right. Only one mechanistic step. What's it called? No intermediates. It's bimolecular. It involves two chemical entities, the base, proton transfer, loss of leaving group. Okay. Radiochemical outcome. Let's look at this. Okay, E2 is a one-step concerted reaction. That's the keyword. Base proton removes the beta proton. E1 is two-step. The leaving group leaves, and then the carbocation forms. So it's like the SN1. Base removes beta proton. Zaitsev and Hoffman products determines whether the double bond forms more or less substituted. Stereoselectivity and stereospecificity. E2 can favor trans or reverse cis, or be constrained to one product due to geometry, anti-paraplanar. Substitution versus elimination, set by the base/nucleophile strength, sterics, solvent, and substrate type. 20 questions, okay. E2 reaction elimination. E1 two-step elimination. The Zaitsev product, the more substituted alkene. The Hoffman product is the less substituted alkene. Alkane, kene, zine. Okay. Antiparaplanar is the geometry where the beta proton and the hydrogen and leaving group must be coplanar and opposite for E2 to occur. Stereoselective is a reaction favors one stereoisomer over another. Reaction gives a single stereoisomer based on geometry. Regiochemistry, where the double bond forms in the molecule. Okay. Tert butoxide, a bulky base that favors the Hoffman product, which is the less substituted alkene. And a strong base, poor nucleophile, is a base-only reagent. Nucleophile-only reagent. Okay. Am I looking to work with ML? Yeah, I think that's probably the next course that I'll do after OChem 1 is just a machine learning AI course, understanding how LLMs work. It's not going to, I want to see if there's a definitive test I can take. That's always a nice thing to end each of these challenges with an actual test. By the way, I finished chapter 9, Feynman chapter 9, start chapter 10. I need a tweet. Should start that in a minute since I'm at 56 minutes already for the stream. Yeah, I want to, as a career. I don't know. I think there's a career to be had out of using AI, machine learning, to help a small business. I'm more interested in the pragmatic side of these things. I'm doing this kind of just for fun, but who knows? I have a nice career in education, as a tutor, and I've never had a boss. I've always worked for myself, so it's hard to imagine wanting to be some grunt at a big tech company working in AI or machine learning. In fact, there's a 0% chance that happens. I like spending time with my kids too much. So here, but I just want to understand how stuff works. I'm very curious. So that's what the main reason. Like, if I'm going to be using LLMs every day, I'd like to understand how that tool works. For someday, when my kids ask me or a student asks me, how does this work? I want to be able to confidently explain it. Strong base. Okay. Anyways, I looked at all this. Regiochemical outcome. Got a lot of stuff going on here. Major, minor. Zaitsev, Hoffman. Okay, draw the Zaitsev and Hoffman products that are expected when each of the following compounds is treated with strong base to give an E2 reaction. For the following problems, don't worry about identifying which product is major and which is minor, since the identity of the base has not been indicated. Just draw both possible products. Okay, let's look at the answers, because I don't have any idea how to do this. That's cool, though. Alkyl chloride. Okay, so the Zaitsev. What did it say those were again? It's really helpful having the glossary. That's a game changer, honestly. The more substituted alkene is here, the less substituted is here. Basically, this goes, and I can either get the double bond here or here. I want to ask it why, though. Why is the Zeitz I assume it probably has something to do with the fact that this is tertiary and this is just secondary, this carbon here on the side, or just, one thing attached. Let's see, though. I'm going to go to X also, get ready to make my tweet. Oh, nice. And then my profile. What was I doing this one? Oh, that was just mechanisms, I think. So I should get one for day 16 / chapter 9. I guess I'm like one day behind with these. That's fine. Double bond is between the central carbon and the more substituted carbon that has 2 alkyl groups. It's tri-substituted. More substituted alkene is more stable. Di-substituted, 2 carbon groups. All right, that's helpful. Compose a short tweet thread summarizing what I learned in chapter 9. This will be the last thing I do today. Let's go get it done. I want to get a screenshot of myself making a face. All right, there's my little excited face. Go to screenshots. Bada boom. Okay. SN2 depends on both the nucleophile and the electrophilic center, and has a backside attack like an umbrella flipping, which leads to an inversion of configuration at the chiral center. Depends on only one factor. And leads to, because the attack can happen from either side, if there are tertiary substrates, then it has to be SN1 because there is too much steric hindrance. Okay. A good leaving group is a weak base, which is a conjugate base of some strong acid. It's interesting in particular that F is not a good leaving group because it's too electronegative, while I minus what do good leaving groups favor again? What does a good leaving group favor, SN1 or SN2? Oh, cool. Owen's got some good comments I want to read. He said AI, machine learning, is incredibly confusing. One thing you learned about today was Habsburg AI effect. It references a dynasty in Austria. I know about the Habsburg dynasty, actually, which collapsed due to inbreeding. Well, that's one theory, but yeah. So the theory is basically that if an AI is trained on AI-generated data sets, it's a huge mess of inbreeding and becomes incoherent. Interesting. Interesting. That doesn't actually make sense to me logically. That's sort of a weird metaphor. I don't know why. I guess that's interesting that it depends on humans. That's very thought-provoking, actually. Yeah, hey, we need the diversity of humans to accelerate AI development. Yeah, interesting that we are necessary, that they can't just prompt themselves. It's more essential for SN1. A strong nucleophile favors SN2, while a weak nucleophile favors SN1. Favors by creating a nice environment for carbocations. Environment for nucleophiles to attack. There were a bunch of examples to memorize, sulfonic acids and things like that. Recapping. 4 factors. Substrates. Tweets help me learn. Follow if you're curious about this learning journey and how to optimize what you learn with AI. Post all. Didn't do the best job of explaining it, but the parallel exists. I'm not that informed about the actual dynasty. I'm not that informed either. I just know the Habsburg dynasty is big. I think they actually ruled the Habsburg family across other kingdoms too, outside of Austria, Austria-Hungary. Okay. Great. Crazy eyes in this, but that's fine. Pin to the profile. Pin. Cool. All right. Not getting great engagement on these, but better than nothing. So I think that's it for the stream today, guys. I got through this. I need to do more, move more quickly, but I'll do my best here. And let's see how long the other chapters are. Okay, I got chapter 10, which we'll do tomorrow on day 18. And that leaves 19, 20, 21. 3 more days after that. If I can get to chapter 11 tomorrow, then I'm in decent shape. But chapter 11 is the longest one. It's just so much material, man. Jeez. Okay. So let's go back to the table of contents. Alkynes, kind of long. Alcohols, kind of long. Ethers and epoxides. All the chapters are kind of long. All right. There's no shortcuts here. I'm just going to have to power through. Probably cut down the curiosity checklist a little bit. That's what I think I'd spend the most time on. And do more problem solving. But guys, thank you so much for tuning in. I will see you all in the next one. Stay learning. Peace.